Welcome students, this is the lecture number 24 in which I am going to discuss about how to measure the vertical angles using total station and also how to compute the height or how we get height from total station. The lesson will be discussed under the following heads. First I will introduce about this and then measurement of vertical angle, and then I am going to explain measurement of height using total station, followed by summary, review, question and further reading. And during this discussion also I will demonstrate using the total station how to measure the vertical angle as well as how to measure the height. Now we know that total station measures vertical angle which is in a vertical plane. Actually total station provides us the vertical angle in terms of zenith angle. Now what is zenith angle? Zenith angle is the vertical angle measured with reference to zenith line. So if our instrument is this one and it is perfectly centered, then this is the plumb line. So and the line opposite to plumb line is the zenith line, and we do get the angle if the telescope is pointing towards like this. Suppose this is the object, so and then this is the angle, zenith angle. So actually total station provides us zenith angle and also total station measures the slope distance L. Now from this zenith angle and the slope distance it derives the change in height or vertical height. So this is the fundamentals behind our zenith angle and actually about vertical height. Also we can go get the altitude angle by considering 90 degree minus z. As I told you in earlier classes that before taking any observation using total station we need to go for temporary adjustment of the instrument, means the instrument should be exactly centered over the station as well as it should be perfectly horizontal. So when we make the instrument horizontal plate perfectly horizontal, then automatically the vertical plate which provides us the vertical angle gets in a vertical plane. This is done automatically and there is an automatic system inside it. So by through that automation we get it vertical plate truly vertical. Now in case of total station actually there are two vertical plates that is available in this person, and these vertical plates are placed parallel to each other with a little space in between, and one of the plate is having the marks of gets rotated and it has a pattern of equally divided alternate dark lines and light spaces as we also find in horizontal plane or horizontal circle, and other circle which is stator contains slit shaped pattern which is the same piece as that of the rotor. And whenever we rotate this telescope about its vertical about its horizontal axis, then some light passes, light emitting diode directs collimated light through this vertical circle towards a photodetector cell. When that and this photodetector sense this variation depending upon the degree of variation, and that variation in light converted to electric pulse, that means energy, and then to digital value. So this is the basis behind measurement of vertical angle, and so in case of total station the measurement of vertical angle like its horizontal angle are automatic. So if we make it perfectly horizontal, then and the telescope if we make it perfectly towards zenith direction, then we will get the zenith angle 0 and when we will make it perfectly horizontal the axis of the telescope, then we will get the zenith angle 90 degree. So, in this way we get the vertical angles, but now the vertical angle may be of two types, as we see that in case of total station we do get the zenith angle, and this is if it is above the horizontal line, then it is the as the telescope is pointed from zenith towards horizontal line, the angle will increase from 0 degree to 90 degree, and sometimes it is the angle of depression, so it is called angle of elevation. So, where it is angle of elevation, when the zenith angle is 0 degree to 90 degree, then it is the angle of elevation, and if it is below the horizontal line, then it will get the angle from 90 more than 90 degree to 180 degree. So, this is the angle of depression. This is the most fundamental thing about the vertical angle. So, and the basic behind the measurement of vertical angle is that whenever we want to measure the vertical angle using total station, what we need to do, suppose I want to find out the vertical angle between two points, suppose this one and this one. So, if my instrument is like this, so first this is the target number 1 and this is the target number 2. So, after setting up the instrument on the point about which we want to find out the vertical angle, we will perfectly go for temporary adjustment of total station, and this will make the vertical circle totally vertical. Then we will direct this telescope towards the first point, first target, and we will bisect it, and we will get a zenith angle Z1. So, we will get an angle like this, zenith angle Z1. Then we will change this, and we will focus this instrument to this second point and bisect the second point, and the total station will automatically provide another zenith angle, that is Z2. So, if we note down Z1 and Z2, then this angle can be find out by taking a difference of Z1 and Z2. So, this is the way how we do measure the vertical angle, but in case of total station actually we do not need to measure vertical angle. In fact, it measures the slope distance, and it measures the zenith angle, and from the zenith angle and slope distance there is a program inside the computer, inside this total station, which directly provides the height or difference in height. So, anyway, so let me first show you how to measure the vertical angle using total station. So, as I told you, for making the vertical angle measurement, first we need to make this instrument temporarily adjusted. So, in order to make the instrument temporarily adjusted, first the tripod legs should be well spread as it is shown here, then the foot screw should be kept middle before you fixing it to this instrument tripod head, and then we have to adjust these these legs to bring our circular bubble in between in the middle. So, there is a circular level as I already told, and the bubble should be placed air inside it using these tripod stands in tripod legs. If it is done, then we have to look through this optical plummet to find out whether the center of the instrument is exactly over the center of the station. If it is not, then we have to open it and we have to shift this, and then we can make it. Now already we have done our temporary adjustment, approximate adjustment. So it is now I can find that the bubble is in the middle, as well as the centering is the center of this instrument exactly above the center of the station. So we do not need to do anything more now. Now after that means approximate leveling and centering has been done, now we have to find precise centering and leveling. In doing that, we have to first make the power on, as I have already done in our previous classes. So from there, here this provides us the indication that whether the cross bubble in the x direction and y direction are in the middle or not. So here I can find that the cross bubble is in y direction is okay. So there is a very little adjustment we need to do. Okay. Now another thing I had told you that this part of the display shows it whether you need fine adjustment or not. If it is in red in color, that means there is a need. So we are in need of doing this, and now I have to bring the bubble in the x direction to be at the center. So you can say this indication is blue, that means our centering and leveling is nice now. In this way already now our centering leveling is done properly. Now again I have to look at the, and I can find that the centering is okay. So centering and leveling is fine. Now after this I have to go to the, now I need to go to the main menu. So this is the main menu. Before going further, let me first orient the object, the angle. So I will like to find out the angle, vertical angle between the center of this point and the center of that point. So first I will bisect, I will orient my stay instrument towards this object using the upper plate and lower plate main screw. So now this telescope is perfectly bisected the center of the prism. So now I can start observe. Now if I give the observe, then inside EDM I can make the prism, reflector is prism kept is here. So okay. So I can see the zenith angle for this object is 84 degree 45 minute. Bisecting the instrument to the object, we can directly get the zenith angle. So when it is done, now I can go to the second object, and by opening it I can look at that. So now it is there. So now it is perfectly centered. So we can get zenith angle 81 degree 32 minute 14 seconds. So the difference between these two, we can get the angle difference between these two objects. So this is how we do, this is how we can go for measurement of vertical angle between 2 points. But for total station actually we are not much interested to measure the vertical angle, rather we are interested to measure the height. So let me now explain about measurement of height. Now in case of total station, actually we measure the relative height. Like suppose this is the terrain, and we want to find out the height of any point B suppose, then another point say A, whose height is required to be known. So, instrument will be placed centering on this point whose height is known. So, height of the point A is known. Now, what it is done, this is our total station and this is the height of the instrument. Hold a, suppose we want to go for reflector based height measurement and the reflector is placed at some point. Suppose this is the reflector is placed and this is the height of the reflector, height of the target. Now with this, this is known, height of the target we can measure it, we known, so it is known. Then we do bisect the target. This is the center of the prism, we bisect it using our telescope of the total station. So, if whenever we measure this distance, so we can get this L, this L is known. So, now from this L, if we also, as I have already told, the zenith angle ZAB observed, L is observed. Now, if this zenith angle is known, then we can get the altitude angle within the total station. This program is there, so which computes the altitude angle from the zenith angle. Now, as you know from this, that if we have this sloped distance and the altitude angle, then we will be able to find out the difference in height between this point and that point. So, VAB. So, this is the horizontal line, this is the horizontal line. So, now we can say that the height of the point B is equal to height of the point A plus height of the instrument plus this VAB difference in which is L sin alpha, then minus height of the target. So, if so this is the expression we which the instrument makes use. So, this is a parameter to be input, what is the height of the point in which the instrument has been set up. This is the height of the instrument. Whenever we will set up the instrument, we can find out the height of the instrument from up to this point. We will measure the distance height of this point from the station, and this is the height of the instrument. This is the height of the target. What is the height of this? From this I can get this value. So, this is known. Now, whenever we will make it on and we will bisect the target, and by using the key measure, then a laser beam will go or and it will come back, and from there this L we can get, and also this alpha will be computed from 90 degree minus ZAB. So, in that way whole of this we can find out, we can compute or find out. So, this is the basis behind how we find out the height of a point using the total station. Now, in this case actually we consider that the distance between AB, distance AB is not much. So, by the word much we mean that this line of sight should be straight, and if the distance is more, then the line of sight gets curved due to curvature of the earth, as well as there being we get the refraction. So, when the distance between the station A and B is far off, then we need to consider the line of sight, not the horizontal, not the linear, but it is a curve. So, you can see this figure. So, when the distance is more, then instead of this line, though this is the actual line, but actually there will be level lines. So, in that case the height of the we have to take into consideration the error due to curvature, this is the error due to curvature, as well as error due to refraction. So, one parameter comes into picture, which is plus error due to curvature minus refraction. So, this is the another thing which comes into picture, error due to curvature. Actually the reading is less due to not being, when it is curvature we should get more reading, but so it should be added, and due to refraction actually there is the way. So, we have to add this with respect to curvature. Then in this figure we can see if we want to find out the height of the point x, then and height of the point t is known, so and this is the datum. So, height of the point x will be height of the point t plus height of the instrument t dash, and that will be equal to this point, which is the level line, and then we have to add from here to here. Now, this is the line of sight, actually this is the horizontal line or horizontal line of sight. So, this is the curvature error which we should add to get this, and then this is the distance, this is the horizontal line, this is the slope distance. So, this is our V L from the slope distance, and this angle we will be able to get this thing L sin alpha, and then this is the height of the prism. So, we have to subtract it. So, we can say that height of the x is equal to height of t plus height of instrument plus error due to curvature, and refraction plus VAB sin alpha minus height of the target. So, this error due to curvature and refraction, actually it is equal to 0.067, it is given here 3 d square in meter, where d is in kilometer. So, this is the thing we have to mark. So, now height of the point, like in this case it is the height of A known, height of the instrument known, error due to curvature we can calculate from this, where d is in kilometer, d is actually L cos alpha. So, we know the horizontal distance between the two stations. So, it is known BAB also BAB, sorry, this is not BAB, this is L sin alpha. So, this is VAB. So, this is also known, and height of the target also known. So, in that way when the instrument location and the target location is far off, then we need to take into consideration the error due to curvature and refraction, and the combined error is to be added. In that way we can find out the distance between, we do find out the distance between two stations when it is far off. Total station provides us the height of a point. So what happens, suppose this is the bridge, the corner of the bridge, that means we have the bridge, the cars moves here, we are here, this is the river, this is the river. So we want to find out what is the height of the base of the base. So what we need to do is just exactly this thing below, we should hold our prism, and our total station is somewhere here. So first what we will do, we will first know what is the height of this point, height of target, or height of our this prism we know. We will first measure this value, and then we will bisect the telescope to this point. Now this is the slope distance, and from zenith angle then altitude equal to 90 degree minus alpha, it will be able to compute h2, and then h2 plus height of the target will give you the height of the inaccessible point. So this is a very simple method. So I will like to demonstrate what is the height of this roof. So for that I will first consider the height of this point. This point is height is 1.8 meter. So and from there I can go for that. So how it is done? It is given there. First we have to make the temporary adjustment, already it is done I suppose already, and then we will make it on fine adjustment of the temporary adjustment has been done, it is there. So now what we will do, bisect this telescope to the center of that. So now this is perfectly bisected. Once it is bisected, then I will like to go to the main menu, to the observe menu. So under the observe menu there is a page 1, page 2, page 3. So I will like to go to the page 3, where there is a special function called rem. So once it is there, then now I have to give the input, the height of the instrument, as our height of the instrument is 1.5 meter. So I am giving it 1.500, and the height of the target we are finding it 1.800, 1.800. So okay, now so now you see here that the total station has measured the slope distance as well as zenith angle as well as horizontal angle. So after this I will now go for bisecting the telescope to the roof corner. So now I will go for REM. Now it is measuring and stop, and then it provides us the height of 2.408 meter. So height of this room is 2.408 meter. So in that way we can also measure, we can make use of total station to measure the height of some point which is not accessible. And another point which is important when we will make the total station measurement, to when if we want to reduce the error, and if we want to measure two distances far off, suppose A and B, we should try to place the instrument in between, so that the back side and forward side distances are more or less equal. So if the back side distance and forward side distances are more or less made equal, then the many of the errors will be cancel each other and we will be able to arrive at better height differences. With this I like to conclude today's class. The summary actually total extension does not measure the heights directly, it computes the height from slope distance and zenith angle. Height can be also measured using some for the inaccessible points, and height distances between 2 points having long distances we should apply the error due to curvature and refraction, and the error in measurement in height or difference in height between 2 points can be reduced by taking the backside and foreside distances equal. With this I like to conclude today's class. Thank you.